back to that a few times, but let's just make sure that we got it. It is the longest theorem that we have considered so far. There will be a few of about the same length. So it's a multi-step procedure, but the difficulty is certainly to discover the proof rather than to actually write out the proof. It's two separate challenges. So we went through the first one, and the second one is pretty much just we have written it, and we can just appreciate that that it is rock solid. Okay, and then with that, once the proof is written the right way, you can try to do more with it, and that's what we try to discover how we can recycle and prove more than that. So we notice that square root of 3, square root of 5, square root of 7, they can be proven, irrationality of those numbers can be proven in the same exact manner. So what would be the conjecture based on this on these few observations about such a theorem? So square root of 2 irrational, square root of 3, square root of 5, square root of 7. What do they have in common?
Square root of a prime is
irrational. Square root of prime is irrational. It appears that with changing virtually nothing in our proof, we can demonstrate this fairly easily. This part would have to be rewritten a little bit, divisibility by 3, 5, 7, but otherwise everything works out perfectly well. And that is the thing about proofs, that we can appreciate that if we understand the proof, then you get more from it than it meets the eye initially. So we started with square root of 2, but then we got more. Square root of 6, when the number is not prime, is slightly more challenging because why is, well, let's take a quick look at that. What difference would that make? So it appears that everything else would be the same. So I'm putting 2 here, then I put 3 there, then I put 6 there, right? So I would have 6 here. Okay, 6. So here the product of 2 not divisible by 6 numbers are, now it seems to be working out just fine. So the product of 2 numbers not divisible by 6, say, will not be divisible by 6. It's not true. It could be divisible by 1, divisible by 3, the other by 2, and together they're divisible by 6. So that's where the proof fails. You'll need more work. That little lemma. Everything else appears to be just fine. Whether the number is prime or not, it's equally applicable. But yeah, this is where the problem appears. So problem. So you take your proof apart. It gets you to really to understand the proof in the first place, and then you get more proofs from one. So as you can see, lemma 1 fails. So do you see it, right? Why lemma 1 fails? If I replace 2 with 6. So, well, let me write out just what I did with 3. So the product of 2 numbers not divisible by 3 is not divisible by 3. Okay, divisible by 2 or by 3, it's the same thing, as long as the 2 numbers they're dealing with are prime. But once you put a composite number there, this is not true anymore, and so our lemma doesn't work anymore. We have to do something else. Okay, so maybe we'll look into that later. At this time, let's just assume to take what we can, and that is the square root of a prime number is irrational. That's all. That's all we know. Okay. So any questions about this proof? Okay, so let's continue. Okay. So we'll do more proofs, various types. I want to do geometry now, but first I have this table that summarizes the implications that we have seen. So what I'm talking about is I have two statements, A and B. Okay, and then okay, so I could negate them. Okay, so I have A bar, B bar. Okay, and now I might have an implication. A implies B, and I can reverse it as we have. Okay, so as you can see, I have created a table. I have created a table with 4 cells like this. Okay. So I will start here with A implies B, right? So that is the original. Okay, so let's fix the ones that let's just, or we can just do it mindlessly, pretty much. So the next cell to my right, to your right, will be A is implied by B. B implies A. Oops. What's the name of this?
Converse.
Converse. Okay. Okay, so now I will, then in the next line I have A inverse, B inverse, negation A, negation B, and I have 2 arrows going this straight and going back. Okay, so one of them is familiar. The second line, which one is familiar?
What do you mean by which ones?
There are 2 lines, 2 entries in the second line.
Yeah.
One is familiar and one is not. Which one?
No,
The second one. Second one is contrapositive.
the first one's not a negation.
Well, yeah, you can see that we have, no, it's not. No.
Okay.
So it's called inverse, for whatever reason.
Okay.
Just to have give it a name, so it's called inverse, but it's not the negation. So negation or implication is pretty much when one is satisfied, the other one does not. So it's there is no implication left if you negate A implies B. Negative would be, you remember what, A is satisfied but B does not, right? So there is nothing implies anything anymore. Okay, so just names. So that just to summarize things, so that we can have everything in one place. I think I'll separate these like that. The only thing that worth also discussing here is the relation, just to refresh your memory. What is the relation between the, if any, between these cells? Original and contrapositive are equivalent, so I'll just put a symbol like this. So this means equivalent. So indeed, the contrapositive and its contrapositive is equivalent. What about the what if I go from the original to the right? Converse. What's the relation? Generally speaking, what? From original to converse, what's the relation? Generally speaking, what? No. No relation. Generally speaking, statement and its converse have no relation in terms of being equivalent. Are they equivalent? They're certainly not equivalent. But does one imply the other? No. So pretty much no relation. I don't know how to. So I'll just put it this way and cross it like this. So either one or the other way doesn't work. Okay, so what else? What else do we have if we hold down from the original to its inverse? Once again, no, there is no relation. Well, actually, before we establish that, how do I know? What's the inverse? What's so interesting about the inverse?
Complement?
No, not the complement. Specifically, what's the relation between the inverse and the converse? Forget about the names, just compare. The inverse is what? So that if I go diagonally, what do I see? What has happened?
The contrapositive of the inverse.
Of the converse, right. The inverse is the contrapositive of the converse, which makes them equivalent, right? So we have another equivalent pair like this. Okay, so diagonally these are two equivalent when you do simultaneously reversal of the arrow as well as negation of both the statements. It creates a contrapositive, and we have two contrapositive pairs of each other, by the way. So don't forget that the contrapositive of the contrapositive is the original. So all those in circles, it's the same thing with the converse. But there is no relation between the converse and the original, so then there is no relation between the original and the inverse, right? So, yeah, so let me at this makes them equivalent. Okay. Okay, so there are more of these. Just so if you go vertically or horizontally, it simply does not work. There is, generally speaking, there are no relations. So the point of this was to point out, to write out whatever we can from these two things, two statements and an implication, and then connect them as much as possible in the general, so content independent way. Okay, that's what logic is. So what are those statements are, those propositions, it doesn't matter, these are how they are related, but generally speaking, the other do not, are not being related. So like these two same, these are the same, and the rest is not the same. So generally we have four cells, only two statements, strictly speaking, in terms of being equivalent. Okay, so that is just nice ways to summarize what we have here. So reversal, negation, and produces only one more statement. Okay. Okay. So I want to take a look at some geometry proofs that might be familiar from Euclidean geometry, high school or something. Well, this is the main one you're probably familiar with. The sum of the angles of a triangle is what? What? 180 degrees. Yeah. Okay, so that is the way you would state the theorem, and that's how you would communicate to anybody, because you can say it so quickly, and it's just it's a short sentence. But we want to prove things. So if you want to prove things, that's what we have done previously. Even though there are nothing but words in the statement of the theorem, original statement, we restate it in the form that is simultaneously more logical, more algebraic, and more, I said, set theory-like. So in other words, treat it as a word problem and assign letters to all the quantities, and then try to extract the relation from the sentence itself. So that is a relation. So is stands for equal, right? So there will be an equation, yes. Okay, so I have my triangle, So I'm starting to translate for the purpose of proof. Really not like, even though it's not dissimilar from those word problems you saw in calculus, maybe calculus 1, remember, so you, I don't know, once again, what is the biggest area of a rectangle with a given perimeter, or very, very sentence with no letters or only words, no algebraic terminology. So we do is doing a very similar thing. So we have the triangles. So that is the triangle. Now the angles are 1, 2, 3, right? And what we're saying that the sum of these angles is 180 degrees. Okay, so I'll just state it alternatively with a statement of the theorem. So it's the same theorem, but it is the form that will be convenient for proof. Okay, so suppose ABC is a triangle. Then, okay, so CAB, right? CAB plus ABC plus BCA is equal to 180 degrees. Strictly speaking, so this is how you would state it in like a high school geometry. If you were in a more advanced mathematical way, you would probably replace 180 degrees with pi, and you would be also careful with the angles. So I'm not sure if it came up it did come up at some point in calculus probably that it matters which way you measure the angles, this way or that way. So I carefully wrote them in such a way that I go clockwise. In all three, I go clockwise, and so that's why I end up to 180 degrees. So which means that to take a full trip around the triangle, I'll have to make 3 turns, left, right. So suppose I'm going counterclockwise. Okay, so I'll have to at each angle, at each corner, I make a turn, and I add up those 3 terms together, and at the end result 180 degrees. Right. So that's how I come back. Okay, which is kind of, I'm not sure what it means exactly. So anyway, let's just concentrate on the theorem itself as it stands, and now we are prepared to write the proof. Well, or at least we can try to. So unlike many things in algebra that we have done, we might have to invoke things from elsewhere, meaning maybe theorems, possibly. We have done it once we invoked once the fundamental theorem of arithmetic, and also we invoked the Pythagorean theorem. There won't be any Pythagorean theorem here because, well, we're not concerned with lengths at all. We're only concerned with angles. So, okay, so anybody remembers the proof or the idea of the proof? So I'm not writing the proof actually. I'm still doing analysis. So theorem has been stated. ABC is my triangle. Anybody remembers how to prove it? Well, no. Well, the idea is that what is it called? Is it called full angle? Full turn. Full turn is 180 degrees. So like this. That's the idea. Okay, does it sound familiar, this idea, a little bit? So in other words, if we want to prove that sum of certain angles is 180 degrees, we might try to show that they actually adapt to a full angle, a full turn. That's the idea. So, in fact, I suppose it is the definition of the full angle is that it's 180 degrees. Or definition of the degree is that you take full turn and then divide 180 parts, and that's the definition of the degree. Okay, so once again, let me mark those angles. So this is 1, 2, and 3. Yeah, so. So where would we find the idea then? So you see what the idea is. We want to demonstrate that these three angles add up to a full turn. So this analysis. So idea. So let's show that these three angles add up to a full turn. I will, so just the way to proceed is to bring things together. So bring these angles together. In a way, you could, I suppose, if you had any kind of a if you had like a drawing software, which I don't think I have here, you make 3 copies of your triangle and align them together in such a way that we're bringing vertices ABC together. Okay, let me think I could try to do that. So I'll start with what I already have. Yeah. Okay, and then I will just attach the other 3. Okay, so I just need room for it. So I'll choose vertex C for where I'm going to place all of the rest of the where all A, B, and C will meet together. Okay, so I will then I will erase these. They're not important anymore, right? Okay, so I take the angle C, and then I take the copy of A that I have at the top, okay, copy of the triangle, and bring A to this place. How about, well, I could actually do it in a horizontal manner, like this. Like this. Okay? Okay, so once again, these are not important. But it is important that at this vertex that I chose, it will contain all the A, B, and C. So I'm bringing A, B, and C in one place. A equal B equal C from 3 copies of my triangle. So the guess is that's what we want to demonstrate, but that picture will help us to understand what's happening. This is our, that's also another copy of our triangle. Okay, so then this is yet the other angle. Probably at this point, A, B, and C have disappeared, so just for convenience, let me call them alpha, beta, and gamma. So this is alpha, I'm sorry, that's not alpha. It's alpha, beta, and gamma. Okay, so that's the idea of the proof. So the idea that they have to add up to a full circle. So what it is actually, if you think about it, where the idea comes from, I jumped to the idea straight ahead. Well, we probably could have figured it out. We could have figured it out because remember, the plan is always look at the definitions, and then we would have to. That probably is a more instructive way of proceeding. Is when you look at the theorem and not try to think of geometrically, but follow the procedure. If you don't know the proof right away, what do? You follow the procedure, which is do the definitions. So then you would have at this point look at what is the definition of degree, what is the definition of 8 degrees, and then you realize that we're talking about a full turn. So definition, that's what has happened. Let's suppose that's what has happened. So we, to understand what degrees are, turns out that we just want to show that we want to represent the sum of the three angles as the sum of, as a full chart, which is, if it works out, I mean, it is not obviously that it is going to work out, but it is, at least at this point, it is plausible that they are indeed add up to 280 degrees. Okay? So, if we can demonstrate that this is what we're seeing here is indeed our triangle repeated 3 times, then we are done. Okay, so so the question becomes, why is this true? The picture, that's the geometry. The challenge of geometry is that the picture might fool you. The better your picture is, the more it is able to fool you. So I made a picture as good as I could, copying the triangle itself, but what could have gone wrong, I did copy the second triangle with alpha on the right. That is certainly, there is no trouble, but we need to demonstrate that the one, that upside down triangle, is the same as the original. Okay, so why, well, let me mark it. Let me mark this one. So why is the green one identical to the original? Okay, so let's try to remember what we know from geometry. So how do we demonstrate that the triangle was built in a very straightforward way, right? So let's repeat the procedure. Step number one is I started with the triangle, which is where it was. Then what I did, now that's important. What has happened is the second triangle I built by a shift. I translated it in a parallel fashion, so that my vertex my vertex A would move to vertex C. Okay, and then the third, how did I make up the third? I did not make it from the original. I simply added that straight line above. That's all. Okay, so green one meaning 3. So why is it identical to the original? So let's remember high school geometry. How do we demonstrate that 2 triangles are identical? What? Side, yeah, okay, yeah. Okay, so we know some, it could be angle and 2 sides, or one side, 2 angles, and thirdly, 3 sides. Okay, so these are the 3 possibilities. Which one is it? Which one is it?
Well, we know 2 sides.
2 side coincide already, but we don't know about the third. So it would be satisfactory if we could demonstrate that the angle beta is indeed the same angle as before. Alpha and gamma were given. We simply have the same triangle. We know that. The third, however, was built in such a way that we cannot guarantee that beta is the one angle that we want. So if we can demonstrate that, then we would be done, right? So. I actually had in mind, so that could work out actually, but what I had in mind actually is the third possibility when you show that all 3 sides are the same. So it might be better to actually demonstrate that third, the black missing part, is actually equal to that part at the bottom. So let's say, let me call this say x. That's right, and then that's how you do it. So x, and this is side is actually AC. So we could show. So let me point out what we have already pointed out. So its 2 sides. Its 2 sides are the same as the original, ABC. Okay, the two sides because they're shared. So show that the third x is the same as AC. Okay, so that's the plan. If that works out, then we can conclude from this on. If then the triangle is identical. And indeed, that's how you can demonstrate it. Is not really. So y AC is equal to x. So that's what. So AC is equal to x, or x is equal to AC. You certainly can speak of parallelograms, but there is a similar statement. Probably could refer to as a parallelogram, but it's you can refer to some very basic facts from pretty much Euclidean axioms. So which says pretty much that.
And by AC, you just mean one of those two, like?
No, it is a specific one, right? It is a specific one. It's ABC, our triangle. So AC is that side, the bottom side.
Just one of those things, not the entire bottom, right? I'm not talking about.
I'm talking about the entire bottom of the original, not that new thing. So anyway, I think actually suggestion about the looking at the parallelogram would be better. Why? Because it is very easy to state it in the form of a lemma. Okay, so let's put it in the form of a lemma. A general statement that will be directly applicable to our situation, and then we'll see whether we want to prove that lemma separately or not. So the lemma is about parallelograms. So what do we know? Well, first of all, the definition of parallelogram is that sides are parallel. We already talked about that. So quadrilateral with opposite sides parallel. So and then the conclusion that we care about is about lengths of sides. So how do we put it? Equal, yeah. Yes, in a parallelogram, the opposite sides have equal length. Okay, so the great statement. Certainly, you can prove it based on the Euclidean axioms. But let's just make sure that we know how it applies to our situation. The parallelogram we are talking about is this, or the other one just as well, right? Because both of them are bottom ones. So how do we produce the whole thing? Well, the construction was that it was the second triangle acquired from the first by parallel shift along the AC side AC. Okay, so which means that by definition that new side will be parallel to the original. So unfortunately, I don't have. I probably should mark here. So A, B. So to conclude the proof. So proof of what? Proof of that. We take the lemma. Plus the fact that what is it? It is that the other two sides are parallel. So A is I probably should provide letters here. So maybe A, B, C, D, and E. Okay. So what we're saying here, we need prove that this is a parallelogram. So I have to say that AC is parallel to BD, as well as the last one, AB is parallel to that's a C. AB is parallel to CD. Okay, this way and that way. Okay, So that's what we need. From that, we conclude then by lemma, x is equal to AC. X equal to AC. Then we conclude that triangle BD, what is it? Let me start here. CBD is equivalent or identical. There is no good letter here, so let's just say equal, doesn't matter. To ABC. Okay. So once again, by that logic, that we have more sides equal, two sides they share. The third side, we just prove that it is the same, and we conclude that the whole thing is the two triangles are equal. So that is, by the way, another that I guess this will be lemma 1, and this now we have lemma 2, which is also from high school geometry, which is about solving triangles. So let's state that too. So if you want to really provide every detail, that's what you do. So two triangles with equal sides are identical. Okay. Well, but if two triangles have sides okay, if a triangle has sides equal pairwise to the sides of another, then the two triangles are identical. I'm not sure what language was used in your, did you use the term identical or congruent or what about triangles being equal to each other? Congruent? Congruent is fine. Okay. So we have outlined the proof. What's missing is the one in the middle. AC and AC parallel to BD is and AB parallel to CD. Okay, so referring to our picture. Otherwise, it's the plan is right there. Except we're gonna sort of going backwards. Once we start writing the proof, we will go backwards. But at this time, we still have extra work to do. So once again, AC is parallel to BD, but let's start with the AB parallel to CD. Okay, so the first one is okay. This one comes from by construction, right? So, but by design, so this is by design. That's how the whole thing was constructed, right? So I shifted the triangle parallel. So in a way, I shifted AB in a parallel way, so it will be parallel to AD, right? So that's by design. This, however, the first one, AC and BD, why are those parallel? What? No. Right, but we are trying to prove that it is a parallelogram. So we want to use lemma 1 to prove that sides are equal, and for that we need so we need to demonstrate that this is a parallelogram. So parallelogram has opposite sides parallel. Okay, so and we have one of them have demonstrated these two sides are parallel by design. What about the other two?
See if the diagonal angles are equal.
No, I think it is once again pretty much the same logic. So imagine as the first one, it is a shift. The whole thing is a shift. So you can think about it as if the height of B above AC is the same as the height of D, right? So everything has been shown. Look at the triangle on the left bottom triangle, and what has happened is I shifted the whole thing like this, right? Which means that B was moving parallel to AC, to the bottom. Okay, so that makes it parallel. Okay. So they're pretty much by design too. So that might be, we might need to explain a little bit more when we write the proof with these in the middle. But let's say it seems that all the logic, all the parts we have here are available. So we could try to start writing the proof. Okay, so proof. So starting at the bottom, so moving backwards. Well, unless we want to take care of the lemmas first. Okay, so let's state the lemmas, so we can refer to them as necessary. So, let's say we have stated already them. So this will be the part of the proof. I'm not going to put them inside of the proof as I did last time, because these are actually theorems from high school geometry. We just put here for us to see for reference, but otherwise they exist apart from whatever we are doing here, right? So these are high school geometry, so Euclidean geometry lemmas. It's just a good idea to write them up explicitly. Okay. Okay, so and the rest is here, so that is in the middle. Lemma 1 is combined with the parallel construction, and then we'll hopefully, so this is the what's in the middle between the two lemmas is the main part of the proof. Whatever was elsewhere, it was primarily about the ideas. Okay, so let me try. I will have my paste. Where's the paste? Paste. Okay. So this is my triangle here for reference. Okay. So inside of the proof for the reader to visualize what's going on. Okay. So the construction is that's the tricky part, is to describe the construction properly. So I describe it as a shift of the triangle in the direction parallel to AC. There is a simpler way to describe it slightly, and then let's shift lines in a parallel fashion. So if we, instead of trying to prove that it's a parallelogram, let's just ensure that it is. So what I'm going to do is I'm going to plot a straight line parallel to AB. So let me do it again. Okay. Okay, so I'll have my construction here. Okay, so this is just for reference. I don't want to touch it, so it would be intact for us. So what I'm going to do is I'm going to draw a plane, a straight line through parallel to AB through C. Okay, so step one. So plot maybe not a good language to use. So there is a line through C parallel to AB. Okay? That is Euclid. In fact, one of the Euclid's axioms, sequence. Okay, so there's any point, there's a line, there's a point. We always can plot a line parallel to the line through that point. Okay, so that's what we do. So I take this line, AB line, and this point, and I plot another line. Okay, I'll probably give it a name. How about L? Okay, so we know that they are parallel already. Okay, so secondly, are we gonna, you see what we're gonna do next? Think about it. What? We need a parallelogram.
Just the same thing.
Same thing with the other line, the other side, and the other point. So I write it almost exactly the same thing. There is a line through what? Through what point? B, parallel to AC. Once again, Euclid axiom, and we call it have a good name. M. Okay, so M. So I choose this line, and I choose this point, and then I have my line. M. There might be a simplification. No, there is definitely a simplification here. We are then if we have, we'll do it next time.